we have already discussed, the main problem in the stochastic gradient descent is the convergence. It may be converging sometimes, but it may not be converging all times. So now we have to check whether it is converging or not. In the batch gradient descent, for checking the convergence, if you remember, we have considered the number of iterations on the x-axis and cost function on the y-axis. And if our curve is decrementing, then our learning algorithm is working properly to find the predicted values. So here in the stochastic gradient descent, similarly we are taking the cost function, but in stochastic gradient descent, for each iteration we are only taking one training sample. So we wanted to update the theta for each iteration. Now we are drawing the graph like batch gradient descent, but here number of iterations, for every 1000 iterations we are taking the cost functions of all 1000 iterations and we are doing the average of all cost functions. We are plotting that, and after that again from 1000 to 2000 iterations, again at 2000 iterations we are checking what are the cost functions we have got from 1000 to 2000, and we are doing the average for that and we are plotting. And similarly, if we are using some 30 crores iterations, if we are having 30 crores training samples, then we have to do 30 crores iterations for the inner loop. For the 30 crore iterations, we are taking the graph. On the x-axis, we are having the number of iterations, and the y-axis, we are having the cost function. For every 1000 iterations, we are taking the average of cost functions up to those 1000 iterations. If you can observe here, the graph is decrementing with a slight, you can observe some random increment and decrement. As we have already discussed in stochastic gradient descent, the curve may not be linear always, because we are considering only one training sample. That may lead our cost function. Sometimes it may increment, sometimes it may decrement. But overall, if you see, this is a somewhat decrementing graph. Now, if I decrease the learning rate alpha, this red graph, I may get some better results. My cost function value may decrement. So for the proper results, we can select the alpha value very small. This magenta, compared to this magenta graph, my red graph is having less cost function because I have considered a very less alpha value. Now, why we have to consider for 1000 iterations only? If I take for the 5000 iterations, this graph may look like somewhat linear. You can observe here in the second graph. Yes, if we consider 5000 iterations, for some examples the graph may be linear, but for some examples, in the third example, you can observe. First, I have considered the 1000 examples. This red graph, little bit decrement is there in the cost function. When I have considered the 5000 iterations, then this is giving a straight line. So there is no improvement in the cost function. The reason might be the proper features. We have not chosen proper features, or our alpha is not proper. So it would be better if we restrict our iteration to the 1000 only. Up to 1000 we have to do the average of cost functions. We have calculator for each iteration. Then if we plot our graph, reasonably we can understand whether that is converging or not. Now we will see what if our graph is diverging. Here the cost function, until now, sometimes it may be decrementing and sometimes it may be constant, but now it is incrementing. Because the cost function is incrementing, it is diverging. Why it is diverging? I have not chosen the alpha value properly. Now we have to decrement the alpha value and we have to check whether we have considered the proper features or not. By checking these two factors, we may converge, and sometimes by checking all these factors also we may not converge. Now there is another option with us, decrementing of alpha for each and every iteration. Until now, even in batch gradient descent also, we have advised not to change alpha throughout the iteration. We are taking the same alpha throughout the process. But here we have considered decrementing of alpha, that is also not leading to us convergence, and we have considered the proper features also, but that is also not leading our stochastic gradient to convergence. Now we are checking what is the alternative we have, because the problem is if we do not converge, then even though we are using this much process, we do not get the minimum of the cost function, approximate minimum of the cost function, then our hypothesis cannot be, we cannot use theta naught and theta 1 proper values in our hypothesis, then we may not predict the proper values. So to avoid this, by checking all the factors, if our stochastic gradient descent is not converging, the final option we have is to change alpha for every iteration. How we will change? We will take a constant in numerator and we will take a constant in the denominator, and we will write the iterations. So you can observe I is the iteration. As the number I is incrementing, the alpha value is decrementing. For every iteration, the alpha value is decrementing. This is very good. Then why we are not implementing to stochastic gradient descent automatically? Why we are not making it as a mandatory? Because again, two new terms came, a and b. We have to choose proper values of these two constant 1 and constant 2. Now we are only concentrating on theta naught and theta 1 for choosing proper values. Again, two constants are coming, a and b. If we do not choose proper values of a and b, then alpha may not lead us to convergence. So only when we are not converging, we have used all our options, still our stochastic gradient descent is not converging. At that time, we may choose the alpha constant 1 by iteration plus constant 2. When the iterations, for each and every iteration, the alpha value is decrementing, that may give us a situation where the stochastic gradient descent will take our cost function to the minimum value, it may converge.